So, if you want, I mean,
yeah, yes. Okay, so welcome to everyone, to the people here in the room, and also the people attending remotely. And so we'll have this 4-hour tutorial, so quite long, but also short, because we will try to introduce the topic of geometric learning with some foundations model and also with some applications. So of course, if you have any questions during the talk, please interrupt me and do not wait to the end. So this is more or less what we will talk about. So geometric learning is the term that is used to indicate the applications where the domain of the data is not Euclidean, basically. So in this specific area of research, we are managing graphs, manifold, but also point cloud meshes. And so in this tutorial, it is to introduce, as I told you before, the theory and challenges related to learning from these non-Euclidean data. And then when we will present some architectural solutions. So I try to identify some architecture which is well known and that impose itself as some good architecture. Like for imaging, we have, I don't know, RexNet or LSTM. So some architecture that shown to be effective in this way. In this way, I try to address point cloud, graph, and meshes. And so, as you can see here, this is more or less the outline of my presentation. So, the first part, the first 2 hours, we will have an introduction. Then we will talk about point sets. And in particular, I will present to you a couple of architectures, in particular PointNet and the related architecture PointNet++, and the point CNN. Then, after the coffee break, we will restart with a practical section. So the idea, I would like to show you a Colab implementation for PointNet for 3-object classification. And then in the remaining part of the talk, I will introduce a solution for learning on graphs. And so as a particular case of graphs, we will look into the case of meshes. So I will present to you a couple of solutions also, in this case for geodesic convolution and for spiral convolution. And then the last solution, the last architecture that I will present to you is the mesh CNN, which is another architecture that is employed, which is used to work on meshes. And then at the end, there is some pointer to start reading. Okay, so this is more or less our program for this afternoon. Okay, so let me introduce this topic. Probably you already know something, because the basic concepts are quite simple. So first of all, we would like to make it clear the difference between the image domain, where we have a uniform grid of pixels, and you well know each pixel is associated with a number, and that number represents the color of that pixel or the gray level. So it is called the Euclidean domain because it is basically flat, and we have a regular grid that represents our data. So this is the domain which is more commonly used for images and videos. What happens instead with the geometric learning is the fact that in this case we have a non-Euclidean domain. Because you see on the left we have a geometry. This geometry can be normally it represents, at least in this case, it can represent the shape. So a 3D object in the 3D domain, but not only because, for example, a graph can represent many other things. But in this example, we have the geometry of a shape. So it is non-Euclidean because you see this domain is not flat. So it is a curved domain. So it is normally also referred to as a manifold because it is a variety, mathematical variety in the 3D space. And on the right, of course, we have the pixel domain. So in some sense, the geometry domain is richer because we know everything about the object, about the shape. So we can, for example, account for the volume, for distances on the surface. But instead of 4 pixels, it is just a projection of the geometry on a 2D domain, and so we lost a lot of information. So the idea is that working directly in this domain, we can capture the real essence of the geometry of the world, because of course our world is 3D. And so, as I already introduced, this non-Euclidean domain can be comprises basically point clouds, graphs, but also splines, that mesh, and many other cases. So here we started talking about shape because shape it is something that we know because this context, the shape is refers to basically a natural object or fabricated object that we can manage in the 3D space, but you can see there more accurate definition given by Töndeling, that was one of the first researchers working in this domain, where this shape it seems as something belonging to the natural science, because as I said, the shape is something that belongs to real, even biological elements or fabricated one. In our context, the shapes are mathematical objects, so manifold, as I told you before, that can be modeled in the continuous setting and then transformed to the digital world, translating them in a discrete setting. So the idea is that we, on the left, we have a continuous domain, because in the reality, the domain is continuous. Then the idea is that locally, this domain is approximated by, normally a tangent plane is used, and so we can have a local representation, a local discretization of this continuous model. And so here on the right, you have the digitized form of the shape. So here we start to see some differences between the two domains, the shapes and the images. So you see again on the left, the Euclidean domain is flat. On the right, the non-Euclidean domain instead is curved, so to capture the overall shape of the object. Again, for the 2D domain, we have basically a unique representation, which is given by an array of pixels. So this uniform grid. Instead, as I already mentioned, in the 3D domain, representing shapes, we can have different forms. So we can have a mathematical representation using splines. We can have a graph. We can have a point cloud or a triangulated mesh. So the same shape, the shape is the same, but you see we can have different representation. Again, the parameterization, because for example, for the image, we can parameterize our domain, which is flat and given by a grid using the XY coordinates. So this can be regarded as parameterization. And in the case of shapes, instead, the parameterization normally is just local, because normally we don't have the parameterization which is valid for all the shapes. So we have to represent locally, parameterize locally the shape. And as again, another difference, here you can see transformation, for example. This is another difference that we have between the two domains, because in the case of images, the transformations, for example, are something that you probably have studied in some mathematical courses. So, for example, the perspective transformations or the affine transformation. So the idea is you start from a domain and you preserve some geometric characteristics. For example, you still remain on a plane, but for example, in the perspective case, you have lines that were parallel in the original domain. The perspective transformation, they are no more parallel. In the case of the affine transformation, instead, for example, you preserve the parallelism between the parallel lines in the original domain. And so these are well-defined transformations that we can represent by matrices, because they are at the end a linear transformation. So it is something that we can represent by a 3x3 matrix in the 3D domain. Instead, in the case of shapes, again, the parameterization is general. So it's non-rigid. You see, we have a shape and we can deform that shape in many different ways. In this case, basically, we preserve the geodesic distance that represents the distance computed on the surface, but there are even known transformations that do not preserve the geodesic distance on the surface, so they can be elastic transformation. And so, as an additional difference, you see here for the calculus. So, for example, for images, you can add together two images, so you can compose two images and obtain a different image. But in the 3D case, this is more complicated to define, because if you have two shapes, you see the same object, but in different poles, so you want to sum together and which is the result. So the idea is that these two domains have some similarities, but there is also the impression, the idea that the geometric domain, of course, is more difficult to manage. So here again something about the different representations that we can have. So the most popular are the point cloud triangle meshes, also implicit surfaces, where we will not go into details for this representation, but the idea is that you can represent the shape, the surface, as a function, mathematical function, which is tau equal to 0. But of course, this can be used only for simple surfaces that we can represent in this mathematical form. And then we have other representations, so polygonal meshes, parametric surfaces, voxel grids. This is interesting because if we use a voxel representation, so we represent the value basically, which is contained by a given shape. In that case, we resort to an Euclidean domain, because in that case we have a grid which extends in 3 dimensions instead of 2 dimensions. And so the choice also of this representation can be important for making the success of a particular problem. And so here you can see some examples of these different representations. So again, using volumetric representation, you see, and also meshes. Okay, so this is a very preliminary introduction, and here I wanted just also to point to this work, which is, if I remember well, the first work where this term of geometric deep learning has been introduced. So in more or less 2017, probably there is another paper. This is an extension of another paper, I think, if I remember well, of the same authors that first appeared to the conference. But anyway, this is, you see, there is the authors are Bronson, which is one of the leading researchers in this field, and also Jan LeCunce. Okay, so this is the introduction. So, welcome to this the meeting room that are just arrived, but we just went through a very introductive material. And so now we, as I told you, we try to start talking about point sets. So point sets, basically you can think of point sets like graphs without connection, because we have just points in the normally in the 3D space, but these points could be also in higher dimensional space in the case of a graph. To make it more concrete, more clear for us, if we think this point as the sampling of a given shape. So we have a continuous shape, and we have the sampling of that of the surface of that shape. This sampling normally comes from capturing a device, which can be, for example, a scanner, a laser scanner, or a laser camera. One example is a LiDAR, which is now kept in many cars that try to drive in an autonomous way. And of course, a point cloud can be taken from, for example, from the body of a person. You see here some examples. On the left, we have a synthetic case, and on the right, we have instead the scan obtained with Kinect. Probably you know Kinect now is out of production. That's been substituted by Microsoft Azure. But it's more or less the same. Is a camera which has a depth sensor that can capture the position of points in the 3D space. So the resolution is not very high, because you see here, for example, that probably you cannot distinguish the identity of the person. But anyway, it is interesting because you have this dynamic flow of 3D points, which is in real time. So this device is capable to provide a continuous stream of 3D points. And of course, this can be also very, very noisy. And so here, trying to introduce some more formalism, you see that we can regard this set of points as a graph without edges. So here we have a set of nodes, and for each node, we can assume that we have also a feature vector that in the simplest case can represent the x, y, z coordinate of the point in the 3D space. But for example, we can have also the RGB value, or we can have the normal of the point, or any other feature that we like. So in general, the dimensionality can be n. And so if we consider a set of points, basically the overall set can be represented by a matrix that has a row, the number of, which has a number of rows equal to the number of points, and as a column, the feature vectors in this key dimensional space. You see that in this representation, actually, we have introduced like an ordering between points, but then we will see right now that normally the neural networks that works on this domain should not depend on this order, because if we scan the same object in different time, of course the points have different ordering. So our architecture should be agnostic with respect to the order of the point. This is normally something that we desire with this architecture. And so here you see basically what we want. We have this set of points, so without any connection with these feature vectors. And what we would like to do is to learn, so to have a function that produces an output y from this set of points. And as I just mentioned, the idea is that this function should be more or less independent from the order of the points. So you see, if the point x1 is moved in another position of the space, this should be irrelevant for the architecture. So another way to represent this is using some permutation and permutation matrices. So we can think as we have an operator that is capable to change the order of the nodes. And so you see that if we have n points, the number of possible permutations, of course, is n factorial of n. So it's a very high number normally of possible permutations. So in this example, you see that, for example, the point A in the figure is then mapped to the position 3. And so this vector tries to capture this permutation. So the point B is mapped, which is in position 2, is mapped again to position 2. The point C, which is in the third point, the third position, is mapped to position 4. And again, the point D is permuted in position 1. So we have 1. And finally, the point E is again is permuted in the same position. So this point stays in the same order. And so this vector basically is this operator that captures the permutation between the first set and the second set. So if we have different sets, we can always represent the relation between these two sets using a permutation vector, like in this case. And so at the end, we can also think of the permutation in this way. We can have like a matrix, which is the dimension given by the cardinality of the points. This permutation matrix has just one value for each row, and each row provides us the way we permute the points in the matrix X. So you see that, for example, applying the matrix on the right, we obtain this different permutation of the input sets on the right part here of this form. Okay, so as I introduced before, something that we would like to obtain is the invariance to permutation. So we would like that if we consider that function f over a set, that the function, the output of that function, will not depend on the order. So in an equivalent way, if we apply a permutation matrix, this permutation, the application of this permutation matrix to the input point should not affect the value you see here of the output. And so this is the notion of permutation invariance, and this should be true for all the or I don't know if it's possible to draw
right click on the presentation. Go here.
this one,
Right. Bottom.
this one,
Yes, and the middle one maybe.
the middle
this
one.
That's right. No.
No.
And I think only
No,
the
maybe
next
I
is,
can, yeah, maybe I can
this one.
this one, yeah, to
I think
maybe
only this one
to
without
make
no-
the font, yes. Okay. So with this definition of permutation invariant, the most general form that we can use for let me say a method that tries to learn from this set of points is something like this. So this model is the model called of deep sets, and you see it is something that has been introduced in 2017. Basically, all the solutions that works with the point cloud try to model in a different way the function there that you see as phi and c, because you see this c and phi function are something that can be learned, for example, and multi-layer per second. Here you can see that there is also this aggregation, which is based on a summation. And this is also something that we can relax in the sense that not all the solutions, of course, use a summation, but more in general, we can use, for example, a maximum or an average. The idea, we will go specify it better in the subsequent slides, but the idea is that here we need an operator in general that is invariant to the order. So, for example, the sum does not depend, of course, on the order. The same is for the maximum and for the average. And so you see here, more in general, we can have a permutation invariant operator, which is represented with this symbol here. So this is any permutation invariant operator that we can use here. So we are not forced to use the summation operation. As another important concept, we also have this of permutation equivariance, that then we will, both this concept of variance and invariance and equivariance, we will also find them for the case of graphs. And here the idea is that these permutation invariant models are good when we want to extract, to derive, to learn something at the global level, the set level. Because if we work at the global level, we would like an operator, a descriptor, which is independent from the order of the points. But if we want to an answer which is given at the node level, so suppose a network that should segment a set of points. In that case, we need an answer at the point at the node level. So in that case, we want to be able to identify this node output. So we want to identify outputs at the node level. But if we have a permutation invariant aggregator, actually this output at the node level would be destroyed. So actually, we seek for functions that do not change the node order, but if we do it as here in the bottom part of the figure. So if we apply a permutation to the input, this the result should be the same as if we apply the permutation to the output of this function. Okay, so in this case, we apply the permutation and we permute also the output in the same way. In this case, if we have a function that works in this way, this is called a permutation equivalent, because the meaning is that it permutes in the same way, basically, as the permutation we apply to the input. And we have, as I said before, we would like to have this kind of behavior in the case we want some output at the point level. Because if we want that the answer for a given point remains the same, independently on how we arrange the point. Okay, here just a way to try to make a link between what we are discussing here for the set of points and what we have for example, for classical CNN. Also, in that case, we want some local operations to model then larger scale. So, for example, normally CNN uses small kernels, 3 by 3, but then the network goes very deep to aggregate at the global level. So this is something that also exists in other transformation, for example, in Fourier transform or wavelength that try to capture also the spatial locality. And so trying to model this at a high level for this set of points locality can be obtained if we have a shared function. So this function C basically is something which is shared between all the points, and so we have the same function that is applied to all the points. Then we can stack together this output of this H1, H5 into a matrix, and basically this is the global operator that transforms the set of points. So applying this local operator to the individual points, we can have this equivariant behavior, and then when we stack together this the output, we have this matrix, and this realizes this invariant operator at the global level. And so for learning on set of points, these are basically the two relevant points that we obtain. So we can try to enforce locality in equivariant set function using a shared function C, which is applied to every node isolation. And then to obtain a global behavior, we can stack together this equivariant function. And at the end, we can, in this way, obtain an invariant function at the global level, because here, for example, we have an operator which is independent from the order. As we introduced before, it can be the summation, it can be the maximum, it can be the average, for example. And so this is the general formulation for an architecture that works on point set, trying to preserve this equivariance at the point level and the invariance at the global level. That is normally what we would like to achieve. Okay, so the final slide for this introducing material for point set. So what we have shown here is that we have find a way to have functions that are permutation, equivariant, and invariant. And this deep set formulation basically is the general formulation. Then, as I told you before, there are different implementations. For example, right now we will go through some details for the point net that try to implement this concept in a specific way. There are then other networks that try to do this implementation in a different way. So there is also some more theoretical conclusion that tells us that if we search for a permutation invariant model, it should be possible to express it in this deep set formulation, and we have a proof for this in these two works. Okay, so in summary, also for the attending people that joined us right now, what we did in this half an hour is introduce the context of the domain and some preliminary ideas, some general ideas for point set. And so now what I would like to show you is are some more concrete application for deep sets. In particular, I would like to go into some details for the point net and the point net plus plus, which are two of the most successful implementation of this deep set concept. And so maybe going this way, we can have a concrete realization of this concept. So these are two figures I took from the point net paper. And so you see here that the idea is that the aim of this network is a general set of 3D points. So in this case, we are in the 3D domain, but actually the network can also work for higher dimensionality. And the network is capable to do basically two things. The first one is the segmentations of the object. So we can have a label for each point of the domain. So we can give a specific part label to the points. And so here you see two results for a simulated kinetic stance and some CAD, some modeled object. And here, instead of the right, you see some results for classification. So in this case, actually, here classification is used more like a retrieval problem. So we have this query given by a set of points, and the system can provide a classification score that can be used to retrieve the most similar object in the data. So of course, these are two different tasks because the segmentation one is a local problem, but we have to look at this in what we have seen for deep sets. Is a problem that try to provide an output for every point, and on the right, instead, we would like to have a global result. Also, we would like to classify the overall shape. And so let's go into some details for this network, because maybe we can find here the same concept that I introduced for deep set. You see, this paper has been published in 2017, so is in some sense an old work, but it is used a lot also now. And if you look, for example, in Google Scholar, it receives more than 20 20,000 citations. So it's really a seminal work in this domain. Actually, as we will see, the architecture is simple in some sense because it is based on multi-layer perceptron that works at point level. And then there is this idea of max pooling for capturing the global information. So it is exactly what we have seen for the before for the deep set, because we say that we can have an operator that works at point level and another one that instead try to be invariant with respect to reputation. And another component that we will see is this coordinate transformation, because a common problem that we have to solve in 3D is that the object can have any possible rotation and translation in the space, and so we need normally to normalize that, to make the representation invariant with respect to this geometric transformation.
In the previous slide, may I ask what universal is this context? Use a very simple, use a very similar proof strategy to show the network is universal. In what aspect?
Yes, if you look into the paper, the author tried to show that what they did is something that can go in the framework of deep set. So in this sense, they try to prove that this realization is something that can be regarded in that more general theory, and so as we have seen here, that satisfy these properties of equivariance at the level of points and invariance at the level of the global shape. Because as we will see now, point net satisfies these two conditions of equivariance at the level of points and invariance at the level of the global level of the set of points. Okay, so if you look to the paper, the author tried to cast this implementation in the same frame, as I say. So again, the input is given by a set of points in the 3D space. In this example, but as I told you, we can assume that this network can work also in a more general domain. The main properties that this network realizes is the permutation invariance. So if we have a set of points, the result is invariant with respect to the permutation of the points. So you can order points in any way, as we have seen before. You can apply any permutation matrix, and the result is does not change. And this was not introduced before, but this network is also more or less invariant to transformation. So as I told you, if you take an object, of course, you can, the shape is the same, but you can translate it to space, so the coordinates can be different, and you can rotate the object, but the object is always the same. So the network should be independent, should recognize, should classify the object in the right way, independently from this transformation. And then there is this idea of having some local representation and the global representation for the point. So I think probably it's more clear here. So I will try to provide you some details for the architecture of this network. So first of all, you see that there are two paths here. One is for classification. So we have this classification network in the upper part, and then we have a segmentation network in the lower part of the figure. And these two are two networks that are used for achieving, for realizing this invariance through geometric transformation. And this is applied in two different points on the points, on the geometry of the input, and also on the feature space. But so we can go step by step. I will try to provide you some details on this. So let me start from the classification network. So you see that here basically we can start reasoning the way that we have points that are represented by a three-dimensional coordinate given by x, I, and z. And so first of all, we have this transformation. I will provide you some details on this later. The idea is to normalize more or less the pose. So the idea is to center the geometry with around the barycenter in order to make it independent from the position in the space, and then to have a canonical orientation for the object. So try to normalize the position that's in the space. So this is the part of this input transformation. And then you see there is the idea that we introduced with the deep sets model. We have basically a transformation. In that context was that function of C. In this case, it is a multi-layer perceptron that transforms individually each point in this input map. So this MLP is shared between all the points. And the purpose is to map basically these input points that are in a three-dimensional space in either dimensional space. Then we have another transformations that is similar to the input one, but in this case, this transformation tries to normalize the position of the points, but in the feature space. So here we try to normalize with respect to translation and rotation in the input space. Here, this network tries to do the same in the transformed space with dimensionality 64. Then we have another layer, which is similar to this one, that taking as an input the transformed points with dimensionality 64, again increases the dimension to 1024. But again, we have a transformation which is applied at the point level. So this is again a transformation which is equivariant. So it is something that if you permute the points, provide the same result for individual points. And then the last operation here, which is applied, is the max pooling. This is the other operator that in the deep set model we introduced, the operator that works at the global level and should be invariant with respect to permutations of the points, because here, if you perform a max pooling, the author have tested their model with the different global operator. They tried the max pooling, the average pooling, with the summation, but they found that max pooling in their case is the best one. And so, of course, we retain the output that provides the maximum value among these 1024. And so at the end, the network's outputs here a vector with 1024 values, and this vector is the global representation of the input point set. With these properties, it is invariant to geometric transformation, and it accounts for local information at the actually the local information is more at this level. Here we have the global information, we have a global feature vector. And then, of course, to perform classification. Here we have a layer that that provides as an output the classification scores for the key classes that we want to classify. And so if we, let me come back, for example, here you see that it is basically a realization of this formulation. We have this function C, which is given by the multi-layer perceptron. We have this operator, aggregating operator, which is the max ruling, basically, and here we have the final function that in this case performs the classification. Okay, so here for the classification, okay, there are some details, but of course, I have also here a slide with all the details, but I put it in the slide, but you can find. I think it is not in the original paper, these details, but I found it in some repository on the web. And so here you can see all the details of the network, the MLP for the first transformation, the MLP for the second transformation, the final MLP for the classification. And see here you can also see the transformation. So this is the global, basically the global path in the network for the classification. Okay. Then we can have a look also to the way the authors try to solve the problem of segmentation. And basically, what they do is a combination between a local embedding and the global embedding. So they actually they took this output here. So the intermediate transformation with the dimensionality 6,4, and this is regarded as a local representation of the points. Because here we have local information for each point. And this information is concatenated with this global feature. So at the end, we have a vector which is given, which has a dimensionality of 1088 that captures both the local and the global information. And then for this segmentation part of the network, you see, again, we have the application of a shared multi-layer perceptor, again at the point level. And again, we have another layer with the same idea of having this multi-layer perceptor. And in this case, it is of case tailored so as to have as an output a matrix which has the dimensionality of the number of points, which are the row of this matrix, and of course as a column, so we have the number of classification labels. So we have m classes for the segmentation, labels, and we have n values, and so each point actually will belong to one of these m classes. Okay, so this is the segmentation, and we have this array as an output, and m is the number of segmentation classes. So this is more or less, so you see at the end, the architecture has no special, let me say, plot. It is based on multi-layer perceptor, but they follow this idea of capturing local information and then summarizing this local information at the global level with permutation invariant operator. Okay, for transformation invariance, let me provide you some more details about this transformation invariance. Sorry.
Another question, perhaps in the previous slides. perhaps it's a naive question, but why do we need to rise to first 64 dimensions and then 1024 dimensions and drop back to? Is it just a heuristic to embed in 5-dimensional space, or?
Yes, I can imagine that the author tried, of course, in many cases, different configuration and what they proposed in the paper is the configuration that provided the more and more satisfying result. The only thing that I find in the paper as an ablation study is the comparison between, I didn't report it here in the slide, but if you look into the paper, you find a comparison between using max pooling, average pooling, and the summation as a global operator here. They did not, if I remember well, they did not provide much information about this choice, but I think it's quite normal to make some tentative, some experimental evaluation. But yes, you are right. The idea is to project in either dimensional space where you capture relations between local relations between these points, and so you project in either dimensional space. You don't come back to the dimensional space. So, in general, I think. Okay, I don't know if. Okay, so about the transformation. So as I mentioned to you before, here the idea is to try to have this network invariant to these geometric transformations, rotation, and the translation. And so this network works here, adding as an input the 3D coordinates of the points. And the idea is derived from this work, this partial transformation, partial transformer network. Actually, it's not a transformer, it's a partial transformation network. It's a work. The figure is from this paper, and the work, if I remember well, is probably 2015, 16. It has been proposed as a way to normalize the position of digits. You see here on NIST, you have an input, and you can say that the effect of applying this spatial transform network is that basically to normalize the output, so to make the output independent from the different orientation of data. So it's a problem that we normally have also for images. Sometimes we try to solve with augmentation, so maybe you can apply something like this. And so this is a comparison with other solutions to this. I didn't actually include the architecture of this network. Maybe if you are curious, maybe I have an example here. No, I don't have. Okay, and I was convinced as well. But anyway, it's basically what this network does. Maybe we can comment it here. Is to derive, in this case, a 3x3 matrix, because in the 3D space, any transformation can be modeled by a 3x3 matrix. So what this network does is to estimate a rotation translation matrix that try to normalize the position of the input. So this is basically the purpose. And this network here does the same, but in the feature space. So the idea, this is something more, maybe something not so intuitive. The idea is that they perform this transformation, this normalization of the position also in the feature space with dimensionality 64. So in this case, this matrix will be a 64 by 64 matrix. So the network learns the 64 by 64 transformation matrix. Because of course, this transformation depends on the dimensionality of the space. So in 3D, we have a 3x3 matrix. In 64-dimensional space, we have a matrix which is 64x60. Okay, and so to conclude here, I included again an example of the retrieval, and so again you can see that the network works generalized quite well with respect to the different distances of the same shape of the same object. Here we have some maybe something that can be regarded as a wrong answer, but actually they have this concave silhouette, independent from the fact that maybe they are square or rounded. So actually they are reasonable results. So this is, as I told you, a first example of realization of this deep sets idea. And here I can provide you some details about another work from more or less the same research group that appeared just after the point net, which is the point net plus plus. If you look also to this paper as more than, I think, 15,000 citations, is another seminal work in this domain that tries to solve some of the problems, let me say, limitations of the point net, because actually we have seen that for the point net captured this local information at the point level, but actually it is not capable to, for example, to work with different states, for example, or with different resolution of these of the point cloud. And so the point net plus plus try to provide additional insights, additional improvement in these directions. So this is more or less the figure that, of course, I took from the paper that the author used to motivate their solution. So you see here that for the point net we have that max pooling operation to aggregate point set. Instead, the point net plus plus tries to construct, to derive this hierarchical grouping of points. And so there is the idea of these abstraction levels. So this is set abstraction. And so you see it's a way to construct like a multi-resolution or an analysis at a different level of granularity of this of the original set of points. So basically, a hierarchical structure is constructed with these set abstraction levels. So let's try to understand how, with some details, how this works. So the idea is that these set abstraction levels basically are constructed using these three basic operations or layers. The first one is a sampling layer that selects a set of points from the input. So suppose you have your set of input points at a certain granularity, and you extract just a subset of these. So these points should be like centroids of local region. So this is a sampling layer. Then there is a grouping layer, because when you select this point, then try to group together the neighboring points around these centroids. And so this is the grouping layer. And then after this sampling and grouping, there is a point net layer. So on this grouped set, let me say, we can operate with the point net layer. So at the end, this point net plus resolve to be a combination also of several point net layers on this group of this local region in the original set of points. So you can imagine that, of course, the complexity is much higher here because we have several point net that operate on a smaller set of points, but we have many. And so let me try to provide you with some dates for also for these operations. So you see here the set abstraction level. So we start with the input set, which is given by n points, and the points are represented with d-dimensional coordinates. So these are the coordinates of the space. So for example, in 3D, the x, y, and z coordinates. And then for each point, we can have a feature vector. As I mentioned you before, that can be the color, can be the normal, can be any feature that you want to associate to a given point. Let me know if you want to maybe to make a 5 minutes stop. I don't know.
If you would like, or a 5-minute break.
Or just enough. I don't know people if
Yeah, we can do it if you want, so.
So we have a
Yeah.
break once an hour.
Okay, so let's say.
or maybe let me try to arrive to the end of this.
Yeah.
I have not much, probably 10 slides, and then we have 5 minutes break. Oh, no, why is it prefer? But why is it? So, okay, now. It's a good point also to do it.
Okay, so.
Maybe we can do 5 minutes just to.
Yeah.
Can restart at
Let's.
45.
Yeah.
45, okay. 3:45, so 8 minutes. Yeah, because 2 hours.
Yeah.
It's much. So I mute
Yes.
microphone for 5 minutes. Okay, so I think we can start.
Maybe click the,
Yeah.
yes, now you can. I don't know, like, let me,
Now
and then you can, choose the laser again
again.
to see the pointer. How it's going, yes.
So let's start from this slide here. So as I mentioned to you, we have this set abstraction level, and we have these three basic operations. So let me start from the input of this set abstraction level, as we mentioned before, is given by the set of points, and each point has associated the x, y, z in 3D, or anyway, d is the dimensionality of the coordinate of each point, while c is the feature vector associated with each point. And the output you see is in this case the matrix with dimensionality n prime multiplied by the original dimension, which is not changed, and the dimension of the feature vector, which is changed to this c prime. No? Because of course n prime is the subset of the subsampled points, sorry, and the dimensionality, the d-dimensionality keeps the same. Instead, the feature vector dimensionality is changed because it summarizes the local context of these subsampled points. And so this is the sampling layer. So the way we can do the this part here from anyway, that's not a problem. So you see the sampling layer basically keeps a subset of points, and they, for example, can be derived using the iterative farthest point sampling. It is an algorithm that basically you start with the point that you can take randomly, and then the other point that you select is the farthest one from this set, and then you proceed in this way. So each time you add the point to the set increases, and the next point is the point which is the farthest one from the set. The idea is that in this way you try to sample all the set in the best possible way. And they found that this solution is better, for example, with respect to random sampling, because the coverage of the original set is better. And so this way, we try to sample the original set. Then there is a grouping operation. The grouping operation, the idea is that we want to cluster in some way, to group together the surrounding points with respect to these sampled points. And so this can be done in different ways. For example, you can have a radius, so you can have like a ball and take the points in this ball, or maybe you can instead use a key nearest neighbor to select the closest points. And this can be done, for example, using also different distances. Normally, the Euclidean distance. So, indeed, this is the solution that I mentioned, and the ball query. So, all the points that are within a radius, actually, not all, but the number of points is limited to a value which is key. So, they are the closest key points. And the alternative, as I mentioned, is to use a key nearest neighbor. So, are the closest key points. So here there is also this comment And according to this, using bulk query seems to work better because in this case, the dimension of the region is kept the same, different from the key. So this is basically the way we pass from this input set to this one, to the first abstraction level. And then the point net is applied. So we have the input of the point net layer is represented by these sampled n prime points. And for each of these, we have also the key neighbor, and the feature is the original dimensionality and the feature vector. Of course, the effect of applying the point net is to change this dimensionality. The C prime is the dimensionality after the transformation with the point net. And you can also see here that again to make the operation dependent on the position, the coordinates of the points are centered with respect to the center of mass of the points. Okay, so the idea, as you can imagine, in this way, is that at this point we use the point net, we actually obtain an abstraction because we have a set of points that abstract basically the shape of the underlined shape with a lower number of points and with the transformed features using the point net. This is the idea. And we can do this at the different levels of abstraction. This is basically the main idea of the point net. Okay, so here there are some consideration about the fact that the set of points can have both non-uniform density, so the density of point can be different in different areas, and in addition, we would like a representation that are more or less invariant also with respect to the resolution. And so these point net layers actually combine features from regions of different scales. So there is also this additional modification to the simple use of the point net. So basically, there are two ways to concatenate, to combine together features of different regions. So the first one is this multi-scale grouping. So in this case, different basically radius are selected, and then we extract features for different neighbors, let me say different scales, and then these are concatenated together. So this is called multi-scale grouping because at each level there is also this operation of adding different scales. And yeah, and here instead another way is that of using this multi-resolution grouping. So these are two alternative solutions. In this case, instead, we have a step where from the one level to the other, we just keep some of the, we basically summarize this circle, the points in this circle with a representative one. So these are two different ways of concatenation. And here you can see some output, some outcomes from this network. Actually, the author did not report much figures, so this is one of the figure I took from their paper. And so you see the segmentation result with the comparison with the point net. Ours is the point net plus, and the ground truth, of course, is the reference segmentation, so this is the segmentation task. And so you see that compared to the point net is capable for this segmentation task to separate better some object in the same. For example, here the desk from the door that instead here are merged in the same system. Okay, so this is more or less what I prepare for the point net. That is one of the first example, but as I mentioned, you still remains one of the reference architecture for working with the point set. So if you have a problem where you have to segment or classify a point cloud, you can always refer to these two architectures. And to conclude this first part on the point cloud, I also decided to include here another architecture, which is the point CNN, because here what I think is interesting is it is like different authors try to solve in a different way the problem of aggregating local information. So in the case of PointNet, this is solved using MLP. So this MLP that works locally try to capture this local information. Instead, in this case, for the point CNN, it is interesting to see how the authors here try to derive for this domain a convolution operator that resembles in some way the convolution operator that we have in the Euclidean domain. So here the approach is different, because instead of basing the work on that theory that we say of deep sets, they try to start from what we have for imaging, for the CNN for imaging. And so what they try to do, you see here, is to find an analogy between the convolution in the images and the convolution on point set. Then they define this XComb operator, which is, let me say, the analogy in this domain for the convolution, and then they present they use this operator to derive two architectures, one again for classification and the other one for segmentation. And also this paper you see is from 2018, so just 1 year later at the point CNN, point net. And if you look to the number of citations, also this paper has I think 3,000, 5,000 citations. So it's another architecture that can be useful in this book. So let me try to show you also in this case the basic idea for this network. So you see, as I mentioned here, the authors first try to derive, to show a parallelism between the convolution in the image domain with the convolution that they want to define in the point cloud domain. And so you see, in the image domain, so for the moment we look at the upper part of the figure, we have we have a grid of points. Of course, for an image we have a grid actually of pixels. So these points basically are pixels, are the pixels of an image. And so we have this grid, in this case, for example, of this dimensionality. And for each point, we have a feature vector, which is given by this C1 component. And so you know very well that applying convolution is equivalent to applying a mask that can be convolution nested, which is basically a matrix. In this case, this matrix is 2x2 convolution mask. In general, it has a dimension key. And so when you convolve, what you obtain is another grid, basically, because it's like the next layer, you have a grid with a lower number of points, so you have changed the number of the dimensionality of the output, but for each point, normally you have you have a vector with a different dimensionality. So in that case, those are represented larger to indicate that the feature vector there is larger, it's a larger dimensionality. And so again, you can proceed with this idea of convolving with a kernel. Again, here you have a different kernel with a dimensionality which is key 2 in this case, and then you apply to this grid. And, okay, here I forgot to mention that you see that here the convolution basically summarized with this in this pixel information that comes from 4 neighboring points. And here we apply again the same idea of the 2D convolution. And so these 4 points are aggregated into the center one. And so again, we reduce the number of pixels in this case because we have now 4 pixels. And for each pixel, we have an associated feature with an increased dimensionality. And so the example here uses an R value of 4 for R1, a value of 2 for key, and the value of R2 is equal to 2. So this is something that you know very well. And so the authors you see here in this figure, okay, this is still a comment on what we obtain on the upper part. So normally R2 is lower than R1, and instead C2 is larger than C1. And this is the parallels that the authors here try to do with the set of points, because you see in this case in the lower part of the figure we have a set of points. So you see here that we do not have anymore the grid structure, and here we would like to define, and which is actually the one contribution to this work, this XCOMB operator. And we would like to obtain something like this. So a reduced set of points, and each of these points captures information from neighboring points. And again, applying this same convolution operator applied to the set of points, again, we have another level where we just have 2 points that aggregate information from the neighborhood. And so formally, you see that the input is given by this set of points. They are N1 with this feature. And each point has a dimensionality in the space D. So this could be the X, Y, and Z dimension in 3D. And the feature instead is in the C1 feature space. And again, so this operator that they are going to define, this XCOMB operator, is applied on the original set. And so at the subsequent level, you see here, we have a reduced number of points, which is called the set of representative points from the original set. So we keep just, you see, this point here, this point here, this point here, this one, and this one, a subset of the original point. And for these points, we basically aggregate information from neighboring points. And so the feature associated with each point in this case is large, as we have for the convolution neural network applied on the. And the same happens for the subsequent level. So the idea at the end, also in this case, is quite intuitive because it follows what we have for the image domain. Okay, so here the test just mentioned the values for the specific case. Also, in this case, on the right part of the figure, you can notice that we keep 2 points. So these points are actually the same position as the points in this in the previous layer, but they accumulate information and they derive information from neighboring points. So this is the intuition that I repeat at the end is quite simple. And so, of course, the one first problem that they try to solve is how to keep this, how to select these representative points, because they should be the points that are most, say, beneficial, as it is reported here, or important for the operation of projection or aggregation for neighboring points. And so, also in this case, there are 2 solutions. One is to use a random downsampling, so we can pick the points randomly. And actually, this is used for classification. And the other possibility is to use farthest point sampling, as in the, because we have seen the point net plus plus. And this solution is actually used for the segmentation task. Because in this case, it is more important that the points are distributed more or less uniformly in the set of input points. Of course, there can be other different solutions for this. And here we go to the core of this work, which is how to define this XConv operator, which is the core operator for passing from the level 1, F1 to F2, where F1 and F2, you remember, are this the set of the original points at the previous level with the coordinates and the feature, and F2 is the selected set of representative points with the associated feature. So basically, the XConv operator has to perform this step. So the idea is that similar to CNN, this operator works locally and local region. And you see here that the output features should, of course, capture information from neighborhood points, and they should be associated with the points, the representative points at the new level. So the neighboring points are those at the previous level, so they are P1, and the representative points are said at the next level, so P2. So here, as notation, they use P to represent this selected point, these representative points, and the feature which is associated to the point P is derived by key neighbors, also in this case. Neighborhood points are those at the previous level, so P1. And so at the end, this convolutional operator takes as an input for a point P the points at the previous level and the feature of these points at the previous level. And this N is the set of neighbors of this key neighbor. And you see this set is an unordered set. It's the set of points that are used to compute the information for the representative point. So at the end, this set can be represented as a matrix of points. The dimensionalities are key because key is the number of points, and dim is the dimensionality of the coordinates, basically, of the original point. So we have this matrix P, and we have also another matrix which has the dimensionality key multiplied by C1, where C1 is the dimensionality of the feature vector for the input point. So basically, we have these two matrices that capture the local information for point P. And so, given these two inputs, this F and P, we want to compute the features Fp which are associated to the representative point P. So the Fp basically collects, summarize, project our derivative. You can use different terms, but it is that capture information from these key neighboring points. And so here you can, at the end, see the formalization of this operator, Fp, which is the feature associated to the point P, to the representative point. It is obtained with this operator, and it takes as an input the point, the set, the two matrices P and F that we have defined here, and we have also the key, where key is the convolutional kernel. So it is what we have to learn during the training. So you see, this is a compact way to indicate this operator. So basically, this operator learns the coefficients, the terms of the metric T, starting from P, big P, and big F. And so at the end, the way this is obtained in practice is using an MLP. So an MLP is a multilayer perceptron is applied to the set of points, which are also in this case normalized with respect to the point P. So the Young parameters coordinate to the local reference point. And there is also another MLP that tries to extract information from the point, the neighbor point, and also the feature that we have as an input. And so again, you see that this multi-layer perceptron operates individually on each point, which is similar to what we have seen for point N. Okay, so this is basically the algorithm that summarizes this XCOM operator. So again, you see the input, which is given by actually key is something that we have to compute. P is the representative point, and P and F are the coordinates and the features for the neighbor points at the previous level. So you see here that there are three preliminary operations basically that we commented also in the subsequent slides. The first one basically transforms the coordinate of the points with respect to the representative y, so making a difference. Then we have an MLP that learns from this normalized points, and so extract a feature vector F delta. And then we concatenate this f delta with the original features associated to the neighborhood point. So this is just a way to change basically the coordinate and to transform the geometric coordinate in higher dimensional space to make them comparable to the features. Then here we have this MLP, which is applied to this set of transformant points, and you see that this operator basically learns this transformation, key-by-key transformation matrix, which is then applied to the feature vector, and at the end we have these transformed points. We have also the feature vector that has been transformed according to this kernel that we have learned. And finally, we have a convolution, which is let me say, traditional standard convolution between these two matrices, key, which is the kernel, and fx, which is the transformation of the feature vector. And so this is the way they propose to solve the problem of learning from points following an approach which is more similar to what we use for images. So here we have some more details, but if you catch the idea, basically everything is contained here. Here, the subsequent slide, we have some additional details, but the core of the algorithm is there. So, as I mentioned here, there is some additional details about the lines 1, 2, 3. So, in particular, the idea of referring the coordinates of the points with respect to the representative points. So, suppose that these P2 are two representative points, P1 are the points are the previous level. And the idea in the step 1 is that of making this subtraction is to represent point P1 with respect to P. So they are represented relative to the representative point. And so you see here also the effect of the NLP, which is applied to these differences. This is what we have performed here in the algorithm in this step here. We apply the NLP to the transformed coordinate. So it is something that is performed at this level. For each point, we applied the NLP to the coordinates of the points referred to the representative one. And then we concatenate with the features of that point. And so this is what is performed in step 3. So basically, these figures can be used to summarize steps 1 to 3 of the algorithm. Okay, so this is more or less what probably I already said while commenting the previous slides, so we can go to the subsequent one. Okay. You can see also this comment here that for an input point cloud without any additional feature, so you can also work with a point cloud where you have just the coordinates of the point, and so in that case only the transformation of the points is used. But in any case, this operation is important to increase basically the dimensionality of the original coordinate. So we pass normally from a 3-dimensional space to an higher dimensional space, as we did, for example, also in PointNet. Now you remember we have points and we apply MLP independently to each point to increase the dimensionality. So here we do more or less the same thing with this stuff. And this way, this coordinate is also more comparable with the feature Okay. So to going to the conclusion of this first part of the tutorial, here you can see some additional figures that try to figure out the architecture for the two cases of classification and segmentation. So the figure 1 is the simplest example of a classification point CNN. So you see, we start from a set of points, and using this convolutional XConv operator, we select, in this case, 4 representative points, and we aggregate for each of these information from 4 neighboring points, because key is equal to 4. And 4 is also the number of representative points. And we can do this for several levels. So in this case, we pass from 4 to 1, and again, this point accumulates information from the 4 neighbors. And then at the end, we have a fully connected layer with trained with the loss function to perform the classification. So this is the simplest way that we can apply the network. Actually, authors shown that it is better to work in this following the architecture which is represented here in B. The difference is that here we have like a dilation operator. Maybe I can comment. Yeah, probably. Okay, here maybe we can also mention this concept of receptive field, because you see for the first example, the example in A, so the simplest architecture, the receptive field. So basically, how much of the entire shape it is seen from a point at the subsequent level. This is given by key divided by n, where key is the neighbor point number, and n is the point number in the previous level. And so, if we want to enlarge this receptive field, one thing that the authors suggest is that of using a sort of dilation. You see here that in this solution with the dilation equal to 2, again, this point here keep information from, or this point here from 4 points, but at this level here where dilation is applied here, you see we keep 1 point, and then skip 1 point and keep another one. So in this way, the receptive field is enlarged. So each representative point at the next level can see a larger part of the previous level. But again, we can summarize the set with just 4 points. So we keep the number of points small, but we enlarge the receptive field. And so this can be done with this dilation concept, which is something used also from images. And so this slide comments about this. So we use the dilation solution. You see that the receptive field increases in this case from key divided by n to key multiplied by d divided by n, because we see a larger part of the underlying set of points. Okay, so and the last comment here for the classification part is maybe here the fact that the output is obtained from different points. So normally, instead of having just one point that summarizes all the shapes, normally the author found that it's better to have a set of representative points summarizing globally the shape, even for the classification task, and then so keep the final layer, the points basically that provide the best results. So the normal configuration which is used is this one. So dilation and a number of points at the end, which is not one, but is a larger number. So this is the classification solution. For the segmentation, you see here, basically the segmentation is based on encoder-decoder solution, basically like the UNet, which is a common solution which is used for segmenting images. So you see that many ideas come from as it's normal because it is an easier domain, so many solutions are developed there, and then some author some researchers try to find an equivalent in another domain. And so in this case, the UNet architecture more or less is replicated with this skip connection solutions, and also with the dilation also for the encoder and decoder part. So you see that here we have an encoding in this intermediate representative point. And then again, you can enlarge the set of points with the deconvolution part, the decoder part. And so at the end, you obtain the same number of input points, but with associated basically label for the classification, sorry, for the segmentation task. And so, as I mentioned to you, the design resembles the UNet design. Okay, so I think we are more or less a few slides before the coffee break, so we are more or less on time. So here there is some additional details. For example, dropout is applied before the last fully connected layer to reduce overfitting. So it's a normal use of dropout. And there is also this sub-volume supervision to reduce overfitting. So this is done in this way. In the last convolutional layer, the receptive field is set less than 1. So in that case, only partial information is seen. This is particularly important for segmentation. And so the network is forced to learn more from the partial information during the training. And so in this way, you can try to perform better during the test. But of course, these are all secondary information data. So here they also mention this data augmentation that they found very important to train successfully the point CNN. So they have this shuffle at the random sample of the points in order to make the representation invariant to the order of the points. So again, of course, we want something that is invariant to the sorting of the points. And so this is another strategy that the authors use to achieve this invariance. So to conclude, we have here some results for classification. Of course, I took these tables from the original paper. And so you see, for example, there are many other works, but we can compare, for example, with PointNet and PointNet++. So according to the experiment of the authors on this data set, they are able to of some percentage the result for PointNet++. And for segmentation, we have the authors present similar results. So again, here we have two data sets. This is ShapeNet parts, and we have different measures, and we have this S3 DIS, another data set, and again, this ScanNet. And so they show for all these data set results that are comparable or a bit better than what we will take, for example, for the PointNet plus plus. Okay, so I think this is my last slide, and for this first part, I think we are perfectly on the schedule. So what we have seen this part, just to summarize this introduction to these non-Euclidean domains, and then we focused on the point set that basically can be regarded as a graph without connection. So we have just sparse points in the space with associated features. Then after the half-hour break, we can. The idea is that first I would like to show you also some practice on this. So I prepared a Colab, Google Colab section where I can I can show you the 3D classification part of the PointNet, so we can go through the code and try to run something, and then after that we will focus so on graph and then metric. Okay, so thank you for your attention for this part.
Yes, you can mute.
The microphone. Yeah.
Let's say 4 minutes.
Hello everyone, we wait till 5:05 for the coffee break terminated here. I hope at home you can enjoy also with work.
Check working correctly. Like you can maybe stop the presentation.
for the beginning and then skip the.
Yeah.
Okay.
And then when you close it.
Yeah. We're on the.
Yeah.
So I think we can start. So welcome again to the second part of the tutorial. And so as I told you before, I would like to start by showing a practical section with the Google Colab, where we can start from implementation of point.NET. Actually, this implementation only works for classification, and so we can maybe go through the different steps and highlight some specificity of this domain, and maybe see if we are able to perform the object classification. Actually, the training, as I would show you, is quite slow. I have also pre-training network, but I don't know if we can access it. Let's see. Let's see. So we can access it. So, okay, so here you have the implementation. So I don't know if you are familiar or not with the Colab, but you know it is an environment on Google. So probably you need to log in with your at home or with so here if someone wants to follow, but it is not necessary. Maybe you can do by yourself or offline. Anyway, here you at this link you have implementation. I told you of the point.NET. So you can click and it is shared, so you should be able to run, not I think to modify, but to run the different sections. And here you have also QR code. So let me go to the other slide. So this is just what we have seen. Okay, here we have the classification network that we commented before. So the implementation basically follows this upper part, but we also have this lower part, which is the TNet. Yeah, before I was looking for this one, but I did. I have, so I remember it correctly. So this is the implementation of the TNet. So of this input transform and the feature transform network. You remember we commented about the fact that we needed to align the geometry of the object and also the feature. And this is this transformation network. So you see that what this network does is, again, to increase the dimensionality, to obtain also here a global vector. Then dimensionality is reduced at the end. What is learned is this matrix, which is 1 by 9, because at the end it is a 3 by 3 transformation net. So this is the TNet for the input transform. Then we have a similar network for this feature transform. Okay, and then for testing, as an example, I use this ModelNet 10 dataset, which is a benchmark with 3D CAD models. So they are not scanned objects, but they are objects that have been modeled with the CAD software, basically. And there are two different versions, one with 10 classes and the other one with 40 classes. So, of course, the difficulty of the two tasks is different. In our case, we use the version with 10 classes. So we have 10 categories with this number of models, so about 4,000 for training, and this number of models for testing. So the task is that of classifying each of these 900 objects into the correct class among these 10 10 categories. And the objects are given as a mesh, and they are in off form. So originally we have the mesh structure, but for using the point net, we just keep the vertex, not the connection between vectors. And what else? Okay, this is what I told you before about the time which is needed for the training. So actually, it takes quite a lot of time, because anyway, the point net, is based on a multi-layer perceptron. So the number of parameters, if I remember well, is over 2 million. I don't remember well, but it's a large number of parameters. So you see that the training time is around 20 minutes, at least when I tried on my side for one epoch. And the training, if I remember well, here is for about 20 epochs. So also at home, if you decide to train, you can sometime. Anyway, I have also here a pre-trained network. I don't know if we can use, because actually it was on my drive, so I don't know. But let's try. Sorry. So let me escape from the presentation, actually, and I try to move to the.
It is already on.
Yeah.
Just move your mouse to the right, and it will appear on the second screen. It's
Okay. Okay. So I hope they can see.
They can see.
Okay. So you see, this is the Colab implementation. I used also for a course that I have at my university. So I created this a couple of years ago, starting from the public implementation of PointNet, and it is a solution based on PyTorch. And so we can try to go maybe step by step to
Excuse me.
Yeah.
Perhaps we use some of these.
Maybe
or not.
Professor goes with control and classes. Yes, it is. Maybe one more.
Yeah.
Is it okay with it? Okay. Yeah, you can do it tomorrow. Okay. Okay, so first of all, you have to connect to use the GPU, but in this case, if we do not decide to train the CPU, is not the GPU is not actually needed. Anyway, it should be already set up, otherwise you can go to runtime, and of course I cannot read the Greek, but you can go to runtime, change the runtime type, and set up the hardware accelerator. But normally it is already set up. So here you see in Colab, you can click on this play arrow, and when you have this green sign, it means that that corresponding part of the code has been correctly executed. So first of all, we needed to install some also libraries. So should be anyway quite fast, I think. Okay, and then we initialize this random seed to a specific value. This is important because if you want to replicate the result from one session to another, if you do not start from the same seed, the random number generator, which is used, can of course generate different sequences, so you can compare directly results. So here we decide to start with this seed, and then maybe here it can keep some time, but here we can download the data set.
Don't worry about it.
Okay,
we are on CPU and
we are not using out, and this is the normal, yes. So here we can download the data set as I mentioned to you. Here you should have the link to the data, so maybe we can open up It's not.
Yes, the top link. I'll be the top link. Yes.
Just to have an idea, these are the models that. Oh, sorry, this is an example of processing, but also an example of some of the objects. No, there is not a direct show of the, but here you can download, but we download from the Colab project. So if you click here, the download should start. Actually, it is yeah, quite big, but I see that the download is going faster, so it should not just a few seconds to complete. Yeah, we are at almost 60%. Okay, now it is not done. And you see it is the same, so it's around, yes, almost half gigabyte. Okay, and then we can unzip. Also, this operation can take some seconds to complete. Hopefully, can end successfully. Now, Colab is useful because you can visualize, you can run something without setting up your environment. So here we can set the path to the data, you see, to this model 10. And then here we can prepare the, look at the classes. So you see there is the 10 classes are this one, a bed, for example, chair, desk, monitor, and sofa. So our object that we can have in a room, apartment. So as I mentioned to you before, the format is this off format, which is actually a format where we have a sequence of the position of the x, y, and z coordinates of the points, and then you have also information about how the points are connected. But in our case, for example, here we can read the one-off example to show you the data. You see here we can read this, open this bed of format, and we use just the points, the vertex, not the connection. And so you see, we read, we open, we read the off format, the vertex and the faces, but then we transform faces and vertices in NumPy array, which are the internal structure that are used by PyTorch. And here, if you run this length x, you can have the number of vertices of the shape. So you see that this model has around 2,000 vertex, because x is the first coordinate of the vertex of the mesh. Okay, then here I put this visualization that normally is not necessary, but for our tutorial it's useful, I think, to see a visualization of how the object looks like. And so this function here basically takes as an input the data and visualize the object. So let me see if okay. And here we run the function or the final function. Let's see if this is shown correctly. Yes. Too much.
Scroll back.
So this is one this bad object. So you see, I'm scrolling here, but I think it's quite clear the shape of the object. In this case, we are visualizing actually the mesh, so it appears very well designed, very well modeled. This is bad. Okay, and you see here the coordinates in 3D. So if we rotate, you see that the object has a certain dimension. So, for example, in this Z dimension, it goes from 20 to -20, and here it goes from, for example, along the Y direction between 40 and -40. Okay, so this is the dimension of the object. Okay, here we visualize the shape, but only using the vertices of the shape. So the first thing that appears a bit strange is the fact that this object doesn't look like a bed anymore. The reason is why in this specific object we have large surfaces that are flat. And so to represent those surfaces, it's not necessary to have many points in fact. We have just the corners. For example, here for the surface of the bed, we have probably just the 4 corners, and we have 2 triangles that model that part of the shape. So of course, working with these points is not good, because here we do not have the shape of the bed. So we would like to recognize the bed from these points, probably we will not succeed. Of course, this can be a particular case, because we started from a mesh and we then just use the vertex. But it is just to show you that sometimes in 3D we have to be careful about the specific data that we are handling. And so to circumvent this problem, okay, you see here there is also some comments. So for the vertices, we do not see basically a bed. And so we write here a function to visualize better the point cloud. And then I will show you that we will resample actually the surface in order to have a distribution of points which is more or less uniform on the entire surface. Okay. So this is, if I remember well, it's just for visualization purposes, then we will resample. So this is just a way to resample, so to visualize with the smaller dots. So yeah, because okay. So this is just for visualization. Visualize the shape with the smaller points. But again, we do not have nothing different. It is difficult to recognize a bed from this. So what we do, what we can do, as I just mentioned, is to resample the surface. To sample it, to sample point of the surface unit. This is what we would like to do. And we want to have a uniform distribution of points. And so this is a function to try to sample the surface. So I do not go into the detail of how this works, but you can imagine different ways for example, the farthest point sampling can be a way to sample again, so we can also find this function and then try to use it So you see that here we use 3,000 points to sample the surface, because this is another important thing that with these networks, normally we need to use the same number of points. So each shape should be also represented with the same number of points. While originally they can have a different number of points, but based on the architecture that we have seen before, the idea is that the number of points of the is always the same. So if we do this and sample the shape, you see that it will be shown. Okay. And now, after this uniform sampling, now this is a resemble more better way the shape of the original band. So in this way, we can hope to be able to classify this object correctly. So this is the first point. Another observation is that I made before, the fact that this object has a specific extension, so we can have objects with different dimensions. This is also, for example, we can have another bed with different niches. So normally it is also good to normalize the shape, for example, inside of a ball of radius 1, to avoid these differences in the geometric dimensions of the object. So if I remember well, we should have something also for this. Okay, so the comment now the bed, and now this normalization in the unit sphere. So the idea is that we would like to force each object to be inside of a sphere. So this is the function for normalization. So of course we first send the set of points around the mean, and then we force to be in this sphere. Then we apply this function, and after that we can show again the. And so now, if you look at the here, we see the axis, for example, the x z axis. You see that now the bed has been included in this sphere with the radius equal to 1. So probably we have a radius 1 from the barycenter to from this vertex, for example, this string 1. And so overall, it is included in this. So these are two. This example is useful to understand that we cannot take data and put as an input the network, but we have to do some preliminary work. This is something that some cases we do also for images. In this case, also it's very important. Then here we have also some augmentations. I did not mention it, but of course it is something that is always useful, because here we are seeing that the number of training models is around 4,000. Probably they are not enough, those to make the network also more robust. We added some random rotation and random noise we added some random noise to the points. So it is important also, because if we have random rotation, we have that network that try to compensate and normalize with respect to the different rotation. So we can, if we have different rotation, we can trace better that part of the network. So we have the random rotation here. So you see the 3x3 matrix here to rotate. Yeah, the standard method rotates in 3D. And here you see the random noise that we add to the coordinates. Then we can apply these functions, and here again we can show I think this is an example of the same point cloud, which is rotated and also with some additional noise. So you see that it is no more perfectly aligned along the axis as the previous examples, and also you see that some points is located some more noisy way, and they are no more distributed on exactly on a plane, no, but there is some displacement. So this is augmentation, so quite standard operation. Then, so this is basically the end of the preliminary processing of the data, and then we can start to basically prepare the data, the format that is required by the network. So we prepare a tensor representation for the network. So of course the data, you see there is the X, Y, and the Z coordinate, and they are put in a structure that the PyTorch can use. This is normally called tensor because multi-dimensional matrix. What is this?
You have like some hidden cells here.
Yeah,
if you click on it, they will open.
Okay. Okay, this is to create the data in the format. This is something that maybe is to organize the data in the different category to put them in the right way. And also we transform the because we resample with those number of 3,000 points, we resample the data, but the network in the paper uses 1,024 points as an input. And so we do here another sampling in order to keep just 1,024 points, just to work in the same way as the paper. Okay. So this is the sampling with this number of points. Okay, so all these steps are repeated for data preparation. So and so at the end you see that and also we have divided the data. We have this number as I mentioned in the slide. So we have this about 4,000 models for training, and we have this 900 for validation testing. Actually, here we use the validation as test, and we have the 10 classes, and okay, and the size is 1,024 by 3. So we have 1,024 points, and each point has the 3 coordinates. So at this point, we can load the data for train and validation. And so here you see the batch size that is used in this example. Then here we have the model. So here, if you want, you can see how in practice the different layers that we have seen in the slides have been implemented. So this is the TNet, so the transformation network, the network that learns that 3 by 3 matrix. So probably not have time to, of course, to go into into details here, but if you want, you can try to make in this one what we have seen in the slide, more or less. Of course, I suppose that for sure there is some difference, maybe small, but normally it's always not exactly the same, but you can more or less find that stuff. And you see this T-net is called basically 2 times, once with the key equal to 3, equal to 3, sorry. That means that if the first transformation network applied to the initial coordinates, and here it is called again with the key equal to 64 when this network is applied for aligning the feature vector rather than the input vector. Okay, so here is a quite standard way we use the PyTorch to have the back propagation there. Okay, so this is maybe we can try also to run this one to see better. Okay. Then after that, here we have the definition of the loss that is used for course the loss in this case is the classification loss. So the loss is for classifying, and here we have the training loop. So maybe here I prefer to avoid. Maybe I can also. I think that since I already run this, we should have the metrics. So I can avoid, because you see here you can have you have a pre-trained model, so you can download here if you're at home you want to work with the native file without retraining. Otherwise, you can run and let the network training for a while. Okay, so we can see here the training for. Okay, here the number is 15 epochs. The training loop, and here you see so I don't run this, but you see the different epochs. So the epoch 1 for the different batch, and you see the loss that decreases, and here you see the validation accuracy, and then the second epoch and the different batch, and again the loss that again.
You stop the thing here.
I stopped. Probably.
Yes.
Let me see if yeah, maybe so. Okay, so probably maybe yesterday in the open I tried and I stopped because it required too much time. But anyway, you have an idea of the output that you can expect from the net. And then for the test, okay, here we use some predefined classes in scikit-learn for computing the confusion matrix, because at the end, since it is a problem of classification, we have a classification matrix. And okay, here you see here you have the case where you can load directly the pre-trained network. Okay. I'm sorry, I cannot run this. And here you see the test. And at the end, the confusion matrix. So probably we can focus on a bit on the confusion matrix that we obtained, and this is the results for our training and test. So you see of course, the classification metric is a square matrix where we have the 10 classes, both on the row and the columns. So on the diagonal, you have the shapes that are correctly classified. So you see that for some classes, for example, here we have a perfect classification. For some other, we have results that are not very good. For example, here for the test, we have 40% because it is confused with, for example, this one with the right stand and also with table. Probably they are flat, and so they are. Anyway, you have this confusion method. And the interesting thing is that this confusion method has been obtained with the object that have been normalized to the unit sphere. And after that, we also have an example where the confusion matrix has been obtained without the normalization. And also, I don't know, I forgot, sorry. No, I'm wrong. No, I was convinced that because it was an experiment that I did, but no, this is just the absolute number of shapes that have been correctly classified, not with or without the normalization. Sorry. So here, simply the only difference that here we have the number of shapes that are correctly classified and not the percentage. Okay, fine. Okay, that's all more or less. I think it has been useful, especially I think for understanding those parts about the preliminary operations, and maybe I will skip the network architecture somewhere. I don't know, I go, no, maybe I did not pay much attention, but here, for example, you can see the structure of the network with these the linear layers that transform, for example, from the points to a different side and so on. So you can go through the different layers. Okay. Okay, I think we can come back to the presentation. As I repeat, if you want, you can maybe play with this example offline at home. And in the remaining part of this tutorial, I will try to go ahead with the graphs in particular and the meshes, because what we have seen till now is mostly concentrated on point clouds. And so now we try to understand better what happens if we want to include also relational information between vectors, between nodes. So here we have first an introduction on learning on graphs, and then we will focus on meshes. So, okay, about graph, here there is some very basic slide about the relevance of graphs, but you are aware, I think, of this. So graphs are something that is that can be used to model very different things. So, for example, we can have a graph that models the structure of some chemical formula, or a graph can be used to represent the connection between the nodes of a metro line, or for example, here graph can be used to represent the connections in our brain, or again, here you can use a graph to model, to represent a connection between I'm trying to use the highlight, but it doesn't work anymore. But
Do you want to right click anyone? And go this here, right? Yeah, not again. I don't know why.
I don't know why. And so in this example, you can see, for example, the connection between a social network like Facebook. You can have you can use a graph to take into account of this connection. And so here this is just of course some slides to motivate the importance of this research field. So you see, of course, it is also not updated, but it is not very important, just to show that across the years there has been several also magazine, newspaper article reporting about a new discovery obtained by AI, and in many of these cases, a graph have been used because, as I mentioned, they are very good to model very different natural real-world systems or also natural models. So graphs, according to, I took this from this researcher. You can think of graph as one of the main modalities of data we receive from the net, because, for example, normally we do not account for, in our mind, for image, for example, of all the words there of or government or count, but we have some selected concepts that are the nodes of this graph, and then we have some relationship between them. So probably also in the way we model the environment of the world, there is something which is similar to a graph representation. And so graph representation learning is something that critical that we have to manage in the direction of having an artificial general intelligence, so something that can perform, which is the meaning of general artificial general intelligence, something that can perform as well or better than humans on a wide range of cognitive tasks. Okay, so here we can introduce some notations about the graph that we did for point clouds, and you see the difference basically that now we have this set of edges, the E symbol, and of course this is nothing more than adjacency matrix, so a matrix that has a 1 to represent to indicate that there is a connection between the two vertices, and a 0 if there is no connection between the two vertices. This is one of the simplest way that we have to represent a graph. So by using an adjacency matrix. So of course, if two nodes I and J belongs to the set of edges, we have 1, otherwise we have 0. And of course, these edges can have some features associated, but for the moment it is not important. And so again, here we have a link with what we have seen in the first part of the tutorial, because also in this case, our main desiderata are the same. So again, we want permutation, and this permutation can be either invariance or equivariance. Also, in this domain, we would like to achieve this invariance. And so this is a parallel with what we have seen for the point sets. So for, if you remember at the beginning of the tutorial, we have spent some time speaking about the deep sets that are a set of points, and we want to have a function that is applied to this set of points, and basically the result provided by this function, when we apply it to the set of points, is independent from the permutation. And so for the case of graphs, we would like to achieve something something similar, because this case you see on the lower part of the slide and on the left, we have a graph, so we have also these connections between points, and again we apply a function, and we would like that even if we keep basically the topology, this means that we keep the connection. So for example, the node x2 is connected with the x1, x3, and x5, but the position of the nodes is different. So also in this case, we would like that the result is the same. Yeah? So basically, what is mainly relevant here is the connection of the nodes. Yeah. And so here we try to see the same properties applied of permutation variance and the equivariance applied to graph. The main difference here is that the permutations now act on the edges of the graph. So not just on the vertices, but they can also act on the connections, on the links. And so this means that we permute the rows and the columns of the adjacency matrix. Yeah, because you know, the adjacency matrix capture model the connections, and according to the order of the node. So if we permute the rows and columns, we change both the order of the nodes and the connection between nodes. And so what we would like to have for the two invariances is that, for example, if we apply permutation matrix, again P, when it is applied to the adjacency matrix, it is like to apply PA multiplied by the transpose of P. And so if for invariance, we want that if we apply this permutation matrix and we apply both to the set of points X and we apply to the adjacency matrix, then the result doesn't change with respect to the result that we obtained with the original X and the original adjacency matrix. For the equivariance, as for the case of points, when we apply this permutation matrix, you see, when we apply this permutation, the same permutation is applied to the result. So the output is permuted in the same way. So in the first case, we have permutation invariance. In the other case, we have permutation equivariance. Yeah.
I don't know if it's suitable for our study, but shouldn't in general graphs also be invariant to isomorphisms? So it's a stronger assumption to be invariant in graph with respect to graph isomorphisms than to simple perturbation state. This would mean that we would also change the the coordinates without changing the edges.
Normally here isomorphism is not taken into account. So the two properties that are normally required are the two invariants and equivalent. This is normally what is required. Maybe you can try also for a specific application to also specifically require that isomorphism is also a property that is taken into account. Now, for what I know, at least now in my mind the papers that also require for graph isomorphism.
Even in general graph neural networks, it isn't required to serve. I don't know. I'm asking.
And evolution of this stuff. Okay, and so here we tried also to have the concept, to translate the concept of locality in this domain, because on sets the locality is obtained by normally transforming every node in isolation. Or you remember, for example, in the point net, also the tip sets, we have an MLP which is applied individually or in isolation for each point. So here graph instead have a broader context and which is represented by the neighborhood of the node. So we have to define basically which is the neighborhood of the node. So normally the neighborhood is represented by the first ring or the one off. So basically it is represented by the nodes that are directly connected with a given one. So where there is an edge connecting, for example, if we consider the node I, the first ring or the one off is represented by all the nodes J that are connected by an edge with the node I. And so then we can have also some features associated to these to the nodes in this set. And then we can define a local function, this phi, that operates on this local neighborhood. So the idea is that in the sets we operate in isolation for each vertex, each point. In this case, basically a local function operates on a vertex and the one of the neighborhood of that vertex. So at this point, what we have try to construct permutation equivariant functions by applying the local function over all the neighborhoods. So the idea is that this is similar to what we have done for points, because in that case we apply that function on the individual points. Here we can assume to apply this function to the nodes and the neighbor, and then taking these functions in this way, we can obtain this big F function, which is actually equivalent, because to make sure that this is true, it is sufficient that the function phi does not depend on the order of the nodes in the neighborhood. So I try to say it again. So if we can have this function phi that operates locally, and as we did for points, this function should be equivariant, so does not depend from the order, in this case, of the nodes in the neighborhood. And then we can stack this in a matrix to have this global representation of the graph. Okay, so this is basically a representation of what I just mentioned. So we have this node, which is the node xb. So we have this function phi, which is applied to the node, and the one op, which is represented by those blue nodes that are directly connected by an edge with the central node. And the idea is that the function phi makes that node in a transformed space, which is given by this HB, taking into account the node itself and the neighborhood. And of course, we can have different ways in which we perform this transformation. So this basically originates the different methods that we have through on graphs. So you see, a graph neural network, basically, it is something that operates in that way. We have this local representation, so the points and the neighborhood with these adjacency matrix, and then in the latent space we have this transformation and this latent representation HI that accounts for the neighborhood nodes. Of course, we can have the different methods accounts in different ways of the neighborhood nodes. So, and it also depends on the final goal of our application, of our network. So, for example, if we would like to perform a node classification, we can have this solution where the output provides a classification for every node. This is something that we would like to, the possibility, the possible output.
Sorry, question. In this case, the adjacency matrix is always the same. It is not changed. It's only like the descriptor of the node.
Yes, in this case, yes. Okay, yeah. Only the descriptor. And here we can have instead a graph classification. So in that case, we want to aggregate information from several nodes and provide a label, a classification score for the entire graph. So in that case, we need a way here, let's see, for combining with the output for different nodes, because the HI is the output for each node, and we need a way to combine together. Another possibility is that of, for example, predict a link. So this could be a different application where, for example, given a node, we want to predict, for example, if it's something that counts, I don't know, for graph that represent movement in a specific environment. So the graph node, and we want to move from one node to another, we can also try to predict the link between one node and the other. So we can have different, we can try to learn different things on the graph. This is more or less the message here. And so to arrive to a conclusion here, we can try to provide, to sketch up how, which can be the form of a graph or neural network layer. So the idea again is that for having this graph neural network layer, basically it is the biggest function that we introduced before, And this function, as we have seen, should be equivariant. And to obtain this, we normally have some local permutation invariant function phi. So the idea is that again that this function phi that we apply at the node level is invariant to permutation, and then we stack together these answers, these responses for each node. We stack them together and we obtain this equivalent function at the graph level. So putting all the phi together is this graph neural network layer, while the phi function is what is called the diffusion, propagation, or message passing on the graph. And so here the main part of the research is focusing on different ways we can implement this phi function. So this is actually the area of the research. But independently for this, normally we can try to categorize the different proposals for this function phi in three different, let me say, flavors. So it's like three different categories, which are these three basically. So in many cases, if you look for graph neural network, you can have convolutional graph neural network, or you can have attentional graph neural network, or you can have message passing graph neural network. So basically, they differ in the way this function phi operates, because you see here the different formulation, the simple. Now I have one slide for each of the three cases, but you see from this slide that the difference basically is in the way the information from neighboring nodes is accounted. So the first one accounts for just the information which is on the label, which is on the edge in the convolutional version. The attentional one instead accounts for basically a function that this function A, which is related to both the nodes. So the attention basically between capture the similarities between the two nodes through the attention mechanism, and the message passing is the most general one, where we are not, because basically in this case, the attentional part, we have a scalar normally here. In the last case, instead, is the more general one, and in that case, what we learned from the two nodes is not constrained to be a constant. Of course, it's the more general, but also the most computational cost. So maybe I try to arrive at a point here, but maybe if you want to, we can have a very short break, 5 minutes, and then we go to the end. And so, as I anticipated here, we have one slide for these three categories, three flavors of graph neural network. So in this case, the convolutional graph neural networks, basically the features of neighboring vertices or nodes are aggregated with a fixed weight. So that the C is more or less a fixed weight. And also these weights normally depend on the adjacency matrix. So of course, this is the simplest solution, and also actually the solution that can be run more easily. And so in many applications, it is a solution that is quite often employed. In the attentional instead solution, you see here that the main difference is that here we have these attention waves that are computed between two adjacent nodes. And so this is a middle solution between the convolution one and the message passing one. The limitation is that normally here the computation of that attention is something which is which provides a scalar value per edge. And so here in the lower part of the slide we also have some reference. They are not much recent because I prefer to identify some initial proposition, then subsequent works refers or can be cast to this method. And the last one is the message passing solution, where we can compute arbitrary vectors between two adjacent nodes. And so in that case, we are not more constrained to have a scalar, but we can have a vector trying to model the relation between the two adjacent nodes. So this is the most general, but also it can have a problem for scalability or also for learnability. But of course, it's the most general, and so can be used for many contexts like chemistry, reasoning, and also simulation tasks. And here again, we have some reference works for some seminal works on this type of image. So probably this is the right point if you want to make this 10 minutes after 6, we can have just 5 minutes and restart at 6:15. Want just to break something or go to the bathroom or something. Okay, so we are here again for this last part of this tutorial. And so after introducing the idea of a graph neural network, what I would like to show you, to provide you, is are better two examples of performing a convolution on meshes, which are a particular, can be regarded as a particular case of graph at the end. So we will look into two of these. So the okay. So first of all, let me very briefly introduce, or we already introduced, but say something more about the mesh. So basically, a mesh is a collection of triangle mesh, the collection of connected triangles. So you see, you can model a generic shape just by connecting together triangles. Triangles, because of course it's the simplest planar geometric shape that we can use, but we can also have meshes that are made of, for example, quad, not triangle. And so also in this case, you see at the end, it can be regarded as a sort of graph. So we have a connection between the vertices, which are the points on the three corners of the triangles. And so we can basically identify the two things in this mesh. We have the geometry, which is the position of the vertices, the 3D space, and the topology, which is the way the vertices are connected each other. And so here you can see more or less two surfaces that are very similar or most the same, that have been triangulated with different in different ways. So you can have the same shape, but of course you can have vertices in different positions and with different topology, with different connection. So of course, if we want to learn on such structures, we should find a way to be in some way invariant with these different topologies and different so connection between them. So something more about the triangulated mesh. So normally we have that triangles have also an orientation, and the orientation normally is given following the rule of the right hand. So if you basically rotate following the counterclockwise order in the triangles, you have that your thumb is pointing in the direction of the normal, of the positive normal of the triangle. So this is the normal assumption that is made for deciding about the normal and the orientation of the let me say the side of the triangle, which is the positive one, let me say, for the part which is in view of the This is probably more useful for computer graphics applications, but it is something that we could take into account, or maybe we have to be aware of. Normally, when we talk about meshes, we talk about manifold meshes. Manifold means that we only normally work with meshes where for each edge there are only two incident triangles. So one edge is shared between two triangles. If, as in the example on the left, you have three triangles that are sharing the same edge, in that case, we have a non-manifold mesh. You can also look to these properties, like the case when you have a manifold, basically you have something that can be you have a curved manifold, and you can transform it basically in something which is flat. It's a 2D surface. Instead, in that case, in the case of a non-manifold mesh, you have something that goes outside of the surface, so goes in a third dimension. So a manifold should be a surface, at least a 2D manifold, which can be assimilated to a sheet or something which is adjusted to the mesh. And then you see that for a vertex you can have like a fan around of triangles, or you can have an open fan if the vertex is on the border of the surface. And here you have additional examples of non-manifold meshes. So again, in the first case on the left, you have again that edge is shared by three triangles. In the middle case, instead, you have a triangle that have just you see, it's not connected with the other, so just one vertex in common with the other part of the mesh. And the last case, we have a completely isolated triangle. So also in that case, you do not have a manifold mesh. So manifold mesh is something that, as I told you before, should be assimilated like that you can transform basically in a flat surface without this connection, connecting the sort of this surface. And so again, this is the rule for the right hand that I mentioned before. And so you see, you have to put your fingers along the two sides of the triangles, and the direction of the of the thumb is basically the vector product between those two vectors. And you know, the vector product is another vector which is oriented normal to the plane defined by the two original vectors that you cross multiply. So this is just a few concepts about meshes that anyway can be used. And so here, this is the first example that I mentioned. So generalized convolution meshes with the two different approaches. The first one is a geodesic convolution, and the second one is the spiral convolution. So geodesic convolution is actually one of the first attempts that has been done to define a convolution or on a domain which is a manifold. And so you see this work has been proposed 10 years ago, and the authors, one of the authors is again Bronstein, that who is one of the researchers that contributed more to this area of geometric learning. And so here you see from these figures that the idea here is that of defining a way to perform a convolution on a generic surface, so on a generic manifold. And the idea to perform a convolution, or better, to perform convolution, we need to define, given a central point, an area, region around this point, and we need to have some ordering between this region, because this is what we do again for an image. We have a pixel, and we have a region around this pixel, and we can sort, we can order the pixels in this region. And so here you see the overall idea of this convolution on a non-Euclidean domain. And now I will try to provide you some details for each of these different steps. But the idea is that you see we have a generic manifold that in this case is represented by the shape of a body, and we want to perform, we want to learn from this generic surface, and at the end we want to classify. So the input is this mesh, and the output is the shape category. Of course, on the mesh we can also have some features, some descriptors. Here I do not go into details about the descriptors that we can have. This is not much relevant. The most important thing here is to understand how to perform a convolution on this manifold. And to this end, here there are the main idea is to define these local regions where to perform convolution based on the geodesic distance. You know, geodesic is the distance computed on the surface. So Euclidean distance go in a straight way from a point to another one. But if you have to measure a curved surface like the surface of the hair, you are actually, the hair is a sphere, and so it is a curved measure. And so the name geodesic comes from the measure of the hair, because it's not flat. In general, if you want to go from one point to another, we want to measure the distance, we have to follow the profile of the surface. So we want to go from here and here. We do not go in a straight line, but we pass on the surface. This is the geodesic distance. So they use this idea to define this local neighborhood. So first of all, they have a radial coordinate. So they define these row level sets, which are basically the place of points that are at a given distance from the central point. So if we take a point x, the row level set is given by point x prime, which are at a distance, fixed distance rho. And that distance is computed on the surface. So this allows us to have this to circle around any fixed points on the manifold. And then to have this also angular subdivision, basically what they propose to do is to trace some radial direction from the central point at a given spatial angle theta. And so if we go in specific direction, we have some lines on the surface, and these provide us the angular subdivision of the neighborhood of a point. So this is the way they are able to construct these local geodesic polar coordinates on the map. So this is the way we can define this local region. Then the idea here is to perform basically convolution. So you see there the symbol of convolution of the function that we have on of the surface. Of the surface, we can have a continuous function. This function can represent, for example, the coordinate of the points, can represent the color, can represent the normal, or any feature that we can compute on the surface, for example, the curvature, and so on. So suppose that we have a function f on this continuous surface, and then we want to convolve this function with a filter, which is represented by A, and this filter is parameterized by the angle theta and the radius r. So this is the idea. And this is the, this is the convolution operator that you see here in this summation. This D actually is an operator that allows us to sample the function f. It is called the patch operator, and it is used to sample the function in a given point. But it's nothing more than the sampling of the function on the surface. It can be used also to interpolate the function if we have the function defined just in some, for example, if we have a mesh, the function can be defined just on the vertex, and so the patch operator can be used to sample the function between two vectors. And so here you see how the patch operator works. As I just mentioned, it is a way to sample the function on the surface using a Gaussian around the point. So in order to sample, we use a Gaussian function centered around the central point X. Okay, so we have a sampling which is given by this function where the V terms here is computed in this way. But I repeat, it is just a way to sample the function on the surface with the Gaussian. So with these ingredients, basically we are capable to perform this convolution operator because we can define the filter of this neighborhood, and we can sample the function in this point. And so with this operation in our hand, we can at the end find a network which is structured in this way. First of all, there is a linear layer. It is applied to the input mesh, and so this is just linear layer, which is applied to the Then we have the geodesic convolution layer, which is performing the way that I've just proposed to you. The only thing we have to be aware of is the fact that in that definition, we do not have a starting point. I mean, when we define this neighborhood for a central point, we have not the notion of starting, for example, a radial direction in the neighborhood. We can start in the same way from one of these. And of course, this is important because for an image, we have the grid structure, and so we can decide to start, for example, from the pixel that is upper left, for example. But here we do not have the same notion. So what the authors decided here, of course, we can do it in two different ways. One way would be to define the first one based on the first direction, based on some local characteristic of the surface. Actually, the authors here decide to solve this problem by repeating the convolution for a bank of filters that have different orientation. So they perform convolution not just for starting with the predefined direction, but they try with a certain number by sampling the neighbor with different starting rates. And so at the end, they have a bank of filters here, yeah, because they repeated convolutions using different starting rates. Yeah. And then among all these bank of filters that work on this neighborhood, they use the max pooling. So they took the maximum of these filters. So this, of course, again, provides a way to be invariant to different rotations of the object, because the shape of the human there can be positioned in different ways, and so with this approach, they can manage these differences. So this is more or less the solution, because then they have some more. There is some other details in the paper, but I think the interesting idea here is another proposal of a way to perform convolution on a general surface. So the idea is take points, compute neighborhood using these geodesic distances, and then apply convolution in a more or less standard way, with the only alert of be careful about the starting direction, so performing this convolution for several directions, then took the maximum. Then, of course, you can have a classification layer at the end to provide the label of the output. As another proposal here, I put also this work that resulted in a quite successful way of performing convolution, which is specifically adapted to meshes, because the previous method, this one in general, can be applied also to non-meshes, to a general continuous surface, because here we do not have a clear definition of points of connection. We have a continuous domain, and we define these patches on a continuous domain. Here instead, we exploit this method to try to take advantage from the mesh structure, and the way this method exploit in a successful way the mesh structure is this spiral ordering, because the idea here of the authors is that if we consider a mesh, we have, for example, when we take a point, we have a certain number of, we have basically the first ring is called, so the set of points that are directly connected to the central one. And if you take one of these points in the first ring, you can go in, for example, in this case, in the clockwise manner, but you can, of course, select the counterclockwise. You can order the vertex. So, apart from the choice of the first one, once you have choose one starting point, you can then order the other point. And this is what we need again to perform convolution. We need a neighbor which is ordered, which is what we do with the image. So the only ambiguity here is the selection of the first one. So again, one way to solve this is, for example, to compute a local reference system, for example, using TCA or any other method where you can, according to the local shape, define 3 orthogonal axes, and you can take one of the direction of the local reference frame as a starting direction, then you can define this spiral ordering of the vertex. Another interesting thing is that it is possible to order not just the first ring, but for example also the subsequent ring in a quite natural way. So we can have also a different support to compute convolution. Here in this example, here actually the author also showed that they can also account for a delayed convolution, where, as we have seen also in the case of the point CNN, you can enlarge the support of the convolution, sampling, taking 1 point, for example, every 2. So we can perform convolution, keeping the same number of points, but enlarging the receptive field of the central point. Okay, so these are 2 propositions for convolution. One on a general manifold, continuous manifold. The other one on a mesh. So last, we have still 15 minutes. Try to go fast for this last method. Is again a generalized convolution of meshes, which is given by the mesh CNN. This is again interesting because what the authors did here is try to again take inspiration from the image domain to find a way to replicate the operations, for example, particularly the operation of pooling in this domain. So the main contribution probably is the way they define the pooling operation on the mesh. And the idea is to rely on the edges of the mesh. So all the operations take the edge as the main actor, let me say, of this operation. Okay, so here you have a very preliminary sketch of the idea of performing relation of pooling where 2 triangles and one edge which is shared between these 2 triangles is condensed to 1 point, the edge, while the triangles are condensed into edges. In this way, we can go ahead simplifying the mesh, and so passing from a fine mesh to a coarser one, preserving the information on the edges. So, okay, let's skip some detail and go through this point. So again, you start with the mesh. So it's the definition that we have seen also before. We have that the mesh is given by a set of vertices, and F in this case represented the connectivity. So F basically are the faces, so the triplets of vertices for that define a triangle. So we define not as a graph, but as a set of vertices and a set of faces. And also there is this set of edges that is the connection, of course, between the vertices. And so again, you can associate features to vertices, to faces, and to edges. In this case, in this specific case, the edges are associated with some features. And the idea is that these features are in some way invariant with respect to the, for example, the position or the rotation of the mesh. And then the idea of this network is to propagate, to simplify progressively the mesh and to propagate these features that we have at the edge level. And here you see the way in which this is obtained. In particular, the idea is that there are 5 descriptors that are associated to each edge. And all these are independent from the translation and the rotation of the mesh. So 2 of these are, so the first one is this angle between the 2 triangles. Then we have the angles of the opposite sorry, the pointer doesn't work, but anyway, we have the blue angles of the 2 triangles that represent the other 2 features, and the remaining 2 is basically the length of the 8, which is anyway divided by the length of the edge. So, which is called the edge ratio between the length of the edge and the height of the triangle. So the 2 dotted lines. So all these 5 features are independent. Dimension and between is independent from this transformation, which are reported in the bottom of the slide. So translation, rotation, and also uniform scale. Okay, and so with this feature, basically they define a way to perform convolution and also pooling. Because you see, if we consider an edge, the convolution here is based on the side, the triangles that are connected together. So you see we have A, B, C, and D. So the idea is that of ordering goes in this case, the one ring. In this case, we have, of course, potentially different ordering because we can start from a different point. So the other idea is to make the operation independent from this order. So in order to do this, they aggregated the features. So actually, they do not consider A, B, C, D separately, but they use something which is a symmetric function basically. So, for example, they decided to use the sum between, for example, A and C. In this way, the convolution is independent from the choice, and so it becomes symmetric. And so we do not have any more ambiguity here. And so the convolution defined on the mesh is something that is obtained this way. You see there is a term that depends on the edge, and this first coefficient, key 0. Then we have the other 4 terms that depend on the features on the side of the triangles for the kernel key. And you see that the individual terms A1, A2, A3, and A4 are computed in that way. So they are symmetric because we have A minus C, A plus C, B minus D, and B plus D. So in this way, this receptive field is in some way independent from the ordering of these surrounding segments around the edge. So this is the way the convolution operation is defined on the mesh. Okay, maybe this is a detail that we can skip. And maybe we can at least have a look directly here to the pooling operator, because after we have computed this convolution, then we can collapse. So this operation is called edge collapse. We can collapse the two triangles that are incident that share that edge, so they can be collapsed together, and of course the edge also becomes a point. And here you can see the meaning of performing this operation at different steps. So you can see that basically using this convolution and then mesh pooling, we can pass from the original mesh to simplified versions of the mesh. The idea is that these simplified meshes captures the most of the information, both in the features and also in the vertices. The vertices are mostly used for visualization. So the most important thing are the features, but the position of the vertices is mostly used for rendering parts. And so here we have the way the pooling is obtained. So you see here the operation of pooling and unpooling. So when we collapse edges, we perform the average between A, B, and E, so the three sides of the triangle, and also in the lower part we average E, C, and D. So again we have pooling, putting together the local information of the two triangles, and this operation then can be unpooled, and the unpooling is performed in that way. You see that we have the average of P and Q for the edge, and on the side we use the P and Q. So basically in this way we have a redefinition of the operations of convolution again, and also the operation of pooling. This is interesting because it is something that maybe we have not seen in the other approach. And so in this way we can have several layers of convolution and edge collapse. Of course, in doing this, we have to maintain the property of the fact that the mesh is a manifold mesh. Okay, so probably here I have last slide. So the unpooling basically I already mentioned, and then this is the way it is performed. So we are capable both to perform pooling and unpooling. This is, for example, useful for segmentation because again, for segmentation, the architecture that is normally used is the UNet, where we have encoding and decoding. So we have a simplification, and then we have to restore the original hash. Okay, for classification, we also needed to have a global ordering because the simplification is performed according to the magnitude of the descriptor. So the idea is that first we simplify the less important part of the shape, and we try to keep the most important part. And probably I can conclude here with some samples. So this is this slide reports some results for the segmentation task. So you see in the upper part you have the ground truth, the original mesh on the left, and then on the right you have 3 different layers of the convolution and the mesh pooling. So you see that actually the network is capable to provide the correct label in most of the cases to the different parts of the objects, and you also take this idea of collapsing the edges, so simplifying the mesh. That is useful to understand where is the focus, let me say, of the mesh. So which are the most important triangles, and the triangles that instead are simplified. And here you can see some other segmentation examples. So you see segmentation of some human shapes, and here in the figure on the right, the examples are useful to see the robustness to different triangulation. So the idea is that we have the same, you can see now here in the examples, you have the same shape, but with different topology, so with different triangulation. And so we can see that in most of the cases, the network is capable to produce the same result for the segmentation, so the same labels also for different triangulation. Okay, I think that this is more or less the last slide, because here I just put 2 additional readings for this part of performing learning on mesh. So the first one is MeshNet, which is another idea of extending the operation of convolution on a net, and the directly connected work, which is this MeshNet plus, where here the difference is that instead of working with edges, the focus is on faces of the mesh. And as a last reference, I put actually also credits, because some of the slides of figures of the general part, I kept some of them from a presentation of Emanuele Rodola, working at the University of Rome, and also this presentation on graph neural network. And then I've also put some additional reading that are from two are from Bronstein and some co-author, and the other one is also a site from Bronstein about geometrical errors. And so I think that's all. So we are, I think, perfect on time. It's 7 p.m. So it has been a long tutorial. I hope that you, at least it was useful to you to catch some basic idea. Of course, the tutorial cannot say everything, and yeah, cannot expect to learn everything from this talk, but I think it can provide you some pointer to start the investigating on this topic. So thank you very much again to the person here in the room and also the attendee from remote connection. Thank you very much again. Bye bye.
Thank you, Professor.